Thank you. All right. Hopefully that went okay. That was good kind of review on some of the fundamentals of the point kinetics equations and their solutions. Also, just some kind of basics about the definition of reactivity, things that might cause the condition of our reactor to change with time, and then just kind of like the intro question about what we said about feedback last time. And so we're going to kind of continue talking about some of those things. So hopefully, if we had questions about any of those questions, we'll kind of see what those answers should have been as we go through the lesson for today. And I kind of messed up with my PowerPoint slides, and that usually I have the PowerPoint, which is the has the blanks that you guys have. And so today I forgot to save the PowerPoint and it's on my other computer. So I'm just going to do the writing on top of the slides in a PDF document. It should more or less be the same. But yeah, apologies if things are a little off today in terms of like my organization. So yeah, today's lecture 13, we're going to talk about feedback and perturbations. Um, just a friendly reminder that exam 2 is going to be on Monday, which is a week from now. That exam, same format as exam 1. You got a formula sheet on the Google Drive that is going to be available to you on the exam. Make sure you are studying that formula sheet. Make sure you know what formulas are on that formula sheet. Um, and yeah, you don't want to go into the exam blind, not knowing what is on there. Also, be able to kind of like on exam 1, I noticed that some people were like, if I told you that the problem was about a sphere, some people were not writing the right like shape function that would correspond to that geometry. So for any of the things that are like blank, make sure that you know like what those equations correspond to. Same thing with the buckling terms and things like that. And in terms of studying, the exam is going to cover lecture 7 through 13 and problem sets 4, 5, and 6. So knowing how to do the problems in 4, 5, and 6 is going to be really good because chances are, if you understand those problems and can do those, then you're not going to really see anything on the exam that might surprise you, besides maybe derivations. But the derivations that I could ask you about are listed in the review, so make sure that you practice those derivations. And then, yeah, it'll be very similar. It'll be the exact same format as exam 1, where you'll have like the multiple choice questions, the short answer questions, and then some like workout problems, and then a derivation. And there'll also be like 1 to 2 bonus questions at the end. So yeah, make sure you're preparing for that. We'll have our help session tomorrow at noon, so that if there's anything that you're still wondering about, like with respect to those problem sets, that would be a good time to ask any of those kind of lingering questions, because that'll be the last help session that we have before the exam. So yeah, and if you have any questions about the exam, about the contents of the exam, or about those problem sets between now and then, be sure to let me know. So last time we had kind of started talking about what is feedback. When we use those point kinetics equations, there's a reactivity insertion that rho 0, and those equations will tell you how the system would respond to a reactivity insertion without feedback. But in reality, our reactors do have feedback, and so that is going to occur because when you make some change to your system, it's going to impact other things that might end up influencing if you have some reactivity insertion or some reactivity removal, there's going to be changes to the system that occur as a result of that reactivity change, which will then end up affecting the reactivity again. So that is what feedback is about, how some change in the reactivity might end up impacting the reactivity because of how the system responds to that change. And a lot of those effects are due to temperature changes. When we talk about a reactor, it's a thing that we've engineered so that you take the heat from fission and you turn it into like a useful form of energy. And so the reason that things might change temperatures is possibly because of the heat generation rate. Like if if our fission rate increases or decreases, um, that's what's producing heat, right? Do you remember about how much energy comes out per fission? 200 MeV, right? So every time you have a fission, you release 200 MeV of energy. Most of that goes into heating up the system. And then we talked about how if it's like a large power reactor, like an AP1000, that fission rate is on the order of like 10 to the 10 fissions per second. So you have a lot of fissions happening. Every single fission is releasing energy, and that release of energy in the form of heat can cause temperature changes. And so the fission rate influences your heat generation rate, and the fission rate is based on what your neutron population is doing, what your neutron flux is doing, and also the fission rate depends on the flux and our cross sections. And our cross sections also get impacted by temperature because of things like Doppler broadening and because of expansion and contraction of materials as they heat up or cool down. And if our cross sections get impacted, that means our reaction rates get impacted, and that means that our reactivity can get impacted as a result. Like if we have some temperature change that results in our fission rate going down, then that means that our reactivity is gonna decrease. And so we had kind of illustrated a feedback example where you're imagining that the reactor is like critical, but at a very low power level, so that you're fissioning, but you're not really like increasing or changing the temperature of the system beyond like what the moderator temperature is. And then you're going to imagine that from there, you remove the control rods. And removing control rods reduces the absorption of the system, which is a way of saying that it makes the reactivity go up. So you have a positive reactivity insertion. And what the point kinetics equations say is that if you have a positive reactivity insertion into your system, it's going to cause your neutron population and also your power to increase exponentially. And so that increase in your power is going to cause things to heat up. And when things heat up, it impacts your cross sections. If you think about your cross section, like your macroscopic, oh, let me make this a little bit bigger. Your macroscopic cross section is, oh, that's annoying, is your microscopic cross section times, is it just going to stay like that? Sorry, technical difficulties. Times, dang it, times your numbered density. And so your microscopic cross section that gets influenced by Doppler broadening. Like if you heat up your fuel, that's going to shift your energy spectrum to the right, at least in the thermal region. It's also going to cause Doppler broadening in the resonance region. So increasing your temperature impacts the micro cross section through those phenomena. It also affects the number density, because if you recall, the number density is the mass density rho times Avogadro's number divided by the atomic mass. And so if you have a temperature change, that's going to affect, so rho sub m is the mass density. So, and I'm putting an m there so that we can kind of separate it or realize that it's a different thing from the reactivity, which we also use the symbol rho for, and I'm sorry about that. But yeah, so temperature changes will affect the density of your material, which will also end up affecting your cross sections. And um, so yeah, um, the result of increasing temperature means that you get more Doppler broadening. That means that you get more neutron capture inside of those resonances. And if more neutrons get captured that don't get to go and cause a new fission, then that ends up meaning that the temperature increase results in the multiplication factor or the reactivity going down. So that's an example of a feedback effect because you had a positive insertion that increased temperature and whose result ended up making the reactivity of the system actually go down from where it was before. And as that kind of process continues, eventually with negative feedback, your system will get into a new steady state instead of increasing exponentially forever. And so that's an example of negative feedback. And we design our reactors with negative feedback. We want them to have negative feedback because it gives the reactor stability and it makes the reactors easier to control. And so this is like a feedback diagram that's just illustrating what I was talking about, where you have a reactivity insertion. That reactivity insertion affects the power, thinking about the point kinetics equations. That'll cause the power to increase and make the power, that causes a change in power, which increases the power. That change in power causes the temperature to change and makes the temperature go up. That changing temperature affects my cross sections. It makes my absorption cross section larger. Um, it makes my capture part of my absorption cross section larger, which increases the capture to fission ratio. And that means that as a result, um, you get less fissions that you were having before, and that means that your reactivity actually goes down. So then that decrease in my reactivity impacts what that insertion kind of looks like, which is the example of that feedback loop. And in general, when we talk about positive versus negative feedback, any positive feedback is going to be some change that gets amplified by your system and causes quantities to basically like kind of go and increase without bound, and that makes them very unstable. Whereas with negative feedback, it causes our system to, it kind of dampens whatever that initial impact was, and that makes our systems more stable. So when we are describing what reactivity does to a system or how the reactivity of a system changes because of some input to our system, the coefficient of reactivity is the quantity that we use to talk about that. So by definition, the coefficient of reactivity describes how a change in reactivity can be influenced by lots of phenomena in our reactor. And there's lots of things that can impact our reactivity. Changes in temperature, pressure, the void fraction, the reactor power, all of these things can impact reactivity, and you can have coefficients of reactivity for all of these effects. Um, so in general, this is kind of how we can write a reactivity coefficient in a very general sense, where it's saying the reactivity the coefficient of reactivity for some quantity x, where x could be temperature or power or the void fraction, is the change in reactivity due to the change in that quantity x. And so effectively, you're taking the derivative of the reactivity with respect to whatever that quantity x is. And so this is a derivative, which if you want to take a derivative, you kind of need to know the reactivity as a function of this quantity x. But how about how can I kind of approximate this derivative if I didn't know how reactivity changed with x? Is there a way that I could take this derivative and approximate it? How could I approximate this quantity? Like, if you were like, if you're trying to, if you have a derivative, and you're just trying, and you don't know what the functional form of that derivative is, how might you approximate that quantity? Yeah, so like a Taylor series, and like even kind of if it was a Taylor series with one term, then all you would be doing is basically approximating this derivative as a finite difference, where you would say this is kind of approximately the same as saying just the change in my reactivity divided by the change in this quantity x, where instead of writing it as a derivative, I'm writing it as a change in that quantity, right? It's kind of like when you're in calculus 1 and you think about this is more like the average slope, where this is more like the instantaneous slope at that point. And so if I'm talking about change in a quantity, what is that telling me to do with that quantity? Yeah, exactly. So that would be the same thing as doing my final reactivity minus my initial reactivity divided by my final value of whatever x is minus the initial value of whatever x is. So that that's just the fundamental definition of a reactivity coefficient. And then this is also how we could approximate it if we didn't know what the functional form of how rho changed with whatever this quantity is. And so it's a reactivity change divided by a change in x. So it's going to have units of reactivity on the top, which could be like PCM or dollars. And then it's going to have units of the quantity in the bottom. Like if it's temperature in the bottom, it would be like degrees Celsius or degrees Fahrenheit or Kelvin. So in 7.1 of the Svedkov notes, that talks all about the temperature coefficient of reactivity, which, as the name suggests, talks about how the reactivity of our reactor is influenced by temperature changes. And you can get temperature changes due to a variety of phenomena. Doppler broadening is one of them because that is what's going to happen to our cross section as temperature increases, is that you get Doppler broadening in the resonance region. And then the other thing that changing the temperature does is it's going to change the density. Whoops. Changes the density of our core components. And because the macro cross section depends on the number density, which depends on the density, then temperature changes affect the density and the micro cross section through Doppler broadening. And so yeah, anytime you have a temperature change, you can talk about how that affects the reactivity of the system through the temperature coefficient of reactivity, which kind of, as we were just talking about before, X could be any quantity. So in this case, the temperature coefficient of reactivity is the change in my reactivity, which could be a function of time and temperature divided by the change in temperature. And so the units of this are going to look like reactivity units, like maybe dollars or cents or PCM. And then the units of my temperature might be like Kelvin or degrees Celsius or degrees Fahrenheit. And like ultimately, when we are trying to figure out what a temperature coefficient is, we're mostly concerned with the sign, the SIGN of that coefficient. But we're also concerned about the magnitude of it as well, because some materials in our reactor might have a positive temperature coefficient of reactivity, others might be negative. And in general, what you want is for the sum of those all of those things together to be negative. So when we talk about the sign, that's kind of the more important thing. And we can kind of start understanding that by just thinking about rewriting the definition of reactivity in terms of the multiplication factor. So like if I want to write reactivity in terms of the multiplication factor, what does that look like? Perfect. Yeah, K effective, which could also depend on temperature, sorry, time and temperature, minus 1 over K, which again could depend on time and temperature. So therefore, if we know what the reactivity is in terms of K effective, then we could write the change in our reactivity with respect to change in time in terms of the definition of reactivity in terms of K effective. In other words, this would be the same thing as d by dt of the reactivity, but the reactivity is K effective minus 1 over K effective. So basically, we're trying to take the derivative of, and remember, K is going to be a function of temperature. So we've basically got the derivative of a quotient. And if we want to do the derivative of a quotient, we can either write it as a product by saying it's K minus 1 quantity times K to the negative 1, like writing this as a multiplication where that has a negative exponent, or we could do the quotient rule. I'm going to just think about it as a quotient rule where I'm going to do the derivative of the top, sorry, derivative of the bottom function times the derivative of the top minus the top function times the derivative of the bottom. So if I do the derivative of the if I do low function times the derivative of the high function, then my low function is k effective. And then I do the low function times the derivative of the top function. And the derivative of 1 is 0. So then the derivative of the top function is just dk effective dt, dk effective dt. So that's my low times the derivative of the high function. And then I do minus the high function times the derivative of the low function. So the high function is just that k effective minus 1. And then the derivative of the low function is again dk dt. So I'll have dk effective dt. That's how I learned quotient rule. The mnemonic I learned is low d high minus high d low. So that's exactly what the numerator would be. And then it's all over the low function squared. So then this would be all over k effective squared. And then I just want to like kind of distribute the terms in the numerator, because if I distribute this k effective minus 1 into here, then what I'm going to end up seeing is that the things are going to end up simplifying. I'm going to have a k effective times the derivative of k effective. That's going to be negative. And then, so those two terms, that negative term and this positive term are going to cancel each other out. And then I'm going to have -1 times the derivative of k effective, but then there's a negative in front, so it's really going to be positive. So ultimately, what this is going to look like is 1 over k effective squared. That's supposed to be a square, but it looks really bad. Let me see if I can fix that. Oh no, it's not going to let me. Okay, I'm gonna just, and yeah, apologies for this being kind of messy because I'm clearly not used to doing this in here. So that is not just, yeah, let's ignore that. And I'm saying that's so annoying that it's trying to over. Okay, I'm gonna write it over here. I'm really sorry. So the final result is 1 over k effective squared. Why does it not let me do a square? 1 over k effective squared times the derivative of k effective with respect to temperature. That's that's what the final result is, and that is supposed to be a square. Really sorry that this writing is not cooperating with me. Um, so effectively what we're saying is that our temperature coefficient is equal to this quantity right here. And so notice that k effective squared, even if k is positive or negative, k effective squared is always going to be positive. So then the sign of alpha t is going to be based on the sign of the derivative of k with respect to temperature. So in other words, alpha t is going to have the same sign as this derivative. So k effective must have the same sign as its derivative. Like if the derivative is negative, then the alpha t is going to be negative. If the derivative is positive, then alpha t is going to be positive. So if alpha t is positive, then the derivative is positive, and that means that if I have an increase in temperature, then k effective is also going to increase because the derivative with respect to time temperature is positive. So if I change this by some positive amount, I have to change this by some positive amount for this quantity to be positive. So k effective will increase. K effective increases with increasing temperature if that temperature coefficient is positive. And it's kind of the opposite story if the temperature coefficient is negative, that if the temperature coefficient's negative, overall, this derivative is negative. And so if I increase temperature, if the delta T is positive, then that means that the delta K effective has to be negative for it to overall be a negative quantity. So that means that the K effective will decrease. K effective decreases with increasing temperature if the temperature coefficient is negative. So when we were talking about positive and negative feedback, it kind of goes along with a positive or a negative alpha coefficient. Because think about what it would mean if I increase temperature and that causes K to increase, then that's an example of positive feedback because I increase temperature, which would increase K effective. Increasing K effective would increase my multiplication factor, which would increase my fission rate, which would cause things to heat up more. If I heat it up more, it would cause K effective to go up more. So a positive temperature coefficient means that I have positive feedback. And negative is what we want because that means that if my temperature goes up, it would cause K effective to go down, which would stop things from blowing up out of control. So these kind of go along with each other in that we want our alpha coefficients to be negative because that corresponds to negative feedback. And like I was saying, there's lots of different quantities that we can talk about in terms of their reactivity coefficients. We can talk about a pressure coefficient of reactivity, which would be alpha little p. And the functional form of this result is going to be the same. The same as what I was saying here for the temperature. That if it's a pressure coefficient of reactivity, it's 1 over k squared times the derivative of k with respect to pressure. Um, Pressure coefficient becomes more relevant with gas-cooled reactors versus water cooled reactors, um, because gas pressure the pressure of a gas influences its properties a lot more than changing the pressure of like water. Also, a lot of our water cooled reactors end up being pressurized already, so they're already at a high pressure. Um, and so, yeah, but gas cooled reactors and other reactors have this pressure coefficient of reactivity that is a quantity you would want to be aware of. And with pressure, it's kind of funny too because pressure and temperature kind of go together in a way. So whenever you're talking about the pressure coefficient of reactivity or the temperature coefficient of reactivity, like if you're getting that number from somebody, you need to know, like if you're doing reactor design, you want to know how they actually got that coefficient. Like if it's a pressure coefficient of reactivity, you want to know if that is including a temperature effect or if that was like a isothermal pressure coefficient. If it's a pressure coefficient where temperature has remained constant, or if it was a pressure coefficient that arose while temperature was also changing. Because then you would need to do the temperature coefficient and the pressure coefficient together. Like you would need to add both of those up and consider both of them if you were trying to say like overall what's the feedback of my system looking like. Um, the void, so I'm using V for the symbol for a void coefficient, and that's another quantity that's it's important for us to talk about, especially for boiling water reactors, where you can get where in a boiling water reactor, the coolant comes into the bottom of the core, but the reactor itself is at like a lower temperature, a lower pressure than a pressurized water reactor. And that lower pressure allows for the water to boil as it goes through the core. Um, and so if you think about like the axial height of your core and coolant coming in, it's like pure water when it comes in the bottom, and then you kind of get a quality change as you go up through the core, quality in terms of like the steam quality. And so if if you have water that is turning into steam and forming these voids, if you were to imagine like a void location where there used to be water and now it's like a steam bubble, thinking about how that steam bubble compares to water, do we think that that steam bubble is going to have less or more moderation than just like if water was there? There's going to be less, right? There's going to be less, whoops, there's going to be less moderation because steam is basically just like water with a low density. So if the water is providing the moderation and you have a steam bubble there, it's kind of like you just have less water per unit volume in that location, which means that that water that is there as steam has less ability to moderate and slow neutrons down. How about the leakage? Are we going to have more or less leakage in that void compared to if it was just water there? More leakage, right? Perfect. Hopefully that makes sense. You basically have less material to interact with, so it's going to be easier for neutrons to leak out of that little steam bubble. And How about absorption? Do we think that we're going to get less absorption or more absorption if it's steam compared to water there? Also less absorption. Perfect. And if you have less absorption, that means that you're when you had water there previously and now it's steam, less absorption means that it could mean that um, an increase in temperature is going to cause more voids to form. And if more voids form, but those voids are less able to absorb neutrons, that could end up making our void coefficient positive if it were the case that overall our system still allowed for neutrons to get to like a thermal energy, then having less absorption would mean that the neutrons that would have gotten absorbed in water now stay in our reactor. And if there's some other way for them to get moderated, then having a void coefficient, it's because of this phenomena where you get less absorption in those voids, it lead to the void coefficient being positive. But it kind of depends on the size and position of the void, as well as if there's any other materials in our reactor that act to still cause moderation. Um, and so you can also talk about a density coefficient, which would look very similar, but it would be a confusing equation because you would say d reactivity with respect to density, and you would use the same symbol. So in that sense, it's probably good if you are doing density and reactivity calculations like kind of at the same time to write a subscript m on your row for density so that you can tell like the mass density apart from the reactivity. And so in our reactor, when we think about feedback, there's lots of different materials that respond due to like temperature changes, for example. And we want to be aware of the time scales over which those quantities, those materials are impacted. So like if you think about a solid fueled reactor, which is like most power reactors that we have with those little UO2 pellets, if you have like a solid fueled reactor with a liquid coolant, and the system has a temperature change. Really, if the system has a power change, like if the fission rate goes up, what part of the reactor do y'all think is going to have a temperature change first? The fuel or the moderator? The fuel is going to be the thing that heats up first because that's where the heat is generated. So you have like a power increase, that's going to cause the fission rate in my fuel to increase. That's going to cause first the temperature of my fuel to increase, and then the fuel transfers heat to the coolant. And so as a result of that, if you have some temperature change, the fuel is going to be the thing that responds first, and so it's going to respond more quickly, like in terms of a time scale, than what the moderator does. The moderator will respond to that temperature change too, but it takes a little bit longer for the coolant to change temperature compared to the fuel. So the moderator or the coolant response is a lot slower. So we can almost think of the fuel as like being a prompt having being like a prompt part of the coefficient, and then we can think of the moderator as like a delayed part of the coefficient. And again, the prompt coefficient when the fuel temperature changes, that's going to be due to Doppler broadening in the fuel, whereas when the moderator temperature changes, that's mostly going to be due to thermal expansion of the fuel. So we can break this alpha T up into the alpha T for the fuel and the alpha T for the moderator. So I'm going to say alpha T for the fuel, which could vary with time and temperature, plus the alpha T for the moderator, which again could vary with time and temperature. So that was kind of what I was saying before, is like we have multiple materials in our reactor, and these temperature coefficients, you have to kind of consider all of the different materials that you have. If you consider like structural materials in your core too, those also would have a temperature coefficient, which you could technically include into your overall temperature coefficient. Like maybe there was an extra term that was like plus alpha T for the cladding if you have like steel cladding in your core. So I wanted to talk a little bit more, just to like make sure we're on the same page and understanding about the Doppler effect and Doppler broadening. I wanted to kind of revisit that next. So when we talk about the fuel temperature coefficient of reactivity, it's mostly due to changes in cross sections, which impact the reactivity of our system. So this is a picture of the U-235 um, fission cross section, or sorry, no, this is the U-235 absorption cross section. And what you notice is that the absorption, so the x-axis is the neutron energy, the vertical axis is the micro cross section in Barnes. When the energy is low, these cross sections are relatively high. When the energy is high, these cross sections are relatively low. And then in this like intermediate region, we have all these crazy resonances going on. And so if you were to like zoom in on one of those resonances, this is what those resonances would look like. And this is how those resonances would change with temperature, where this is saying T1 is less than T2 is less than T3. So T1 is like what my resonance looks like at like some cold temperature. And T3 is what that resonance looks like at some hot temperature. So when the temperature is cold, this resonance is like very narrow and high. And as you increase temperature, what you see is that the peak of that resonance decreases, but the resonance itself broadens. So that's what we talk about when we say Doppler broadening. It's physically, these resonances are actually like kind of widening as temperature increases. And these resonances are where we get parasitic capture of our neutrons. It's where they get absorbed and don't end up causing a fission. So if you think about it, the area of the area under each of these resonances is about the same, but you're decreasing the peak and you're spreading out like the resonance itself. And so like if E0 is like the energy of the neutron that would like very easily get captured in the resonance at T1, as I broaden those resonances, it means that neutrons at a wider range of energies are more likely to get caught up inside of the resonance. And so, therefore, as the resonance broadens, more neutrons can get captured inside of that resonance at like a wider range of energies. And that means that more neutrons effectively get parasitically captured when the temperature increases because of this phenomena of those resonances expanding. So if I have an increase in temperature and that results in an increase in the parasitic capture of my neutrons, if the neutrons get captured, they can't go and cause a new fission. So that means that an increase in temperature causes an increase in my parasitic capture, which causes a decrease in my fission rate and therefore a decrease in my multiplication factor. So as a result, the alpha T for a fuel is going to be negative because the increase in temperature is ultimately going to cause an increase in temperature is ultimately going to cause a decrease in K effect. So that's a cool thing about our fuel, at least when you have really it's more prominent with solid fuel, but even if you have liquid fuel, this is still the case. And it means that our fuel kind of has a built-in negative feedback mechanism just because of the physics of Doppler broadening. And so like we could take that temperature coefficient and break it up into a fuel and a moderator coefficient. And the moderator is kind of more complicated because there's lots of different things that affect your temperature of your moderator. Like pressure changes could also affect the temperature because like your water or like a gas, it's like a thermodynamic quantity where the state of that material depends on both the temperature and the pressure. Could also be affected by the void fraction. Um, but in general, we want to just imagine that we're increasing to explain this, we want to imagine that we're increasing the temperature of our coolant in our light water reactor. And if I increase the temperature of my moderator, and here I'm saying coolant, but like if it's a light water reactor, the coolant is the moderator. So the coolant is basically the same thing as the moderator. So here when I'm saying coolant, you can kind of interchange it with moderator if we're talking about a light water reactor. So if I increase the temperature of my moderator, what part of the neutron spectrum, what's that going to do to the neutron spectrum? If I increase my temperature, how does that shift my neutron spectrum? So when I think about my neutron energy spectrum, it's like we're imagining I got this like Maxwellian peak, and then I've got the slowing down region, and then I've got my fission spectrum, where this is like the thermal range, this is like the intermediate range, and this is like the fast range. And so when we talk about the temperature of the moderator, that's really based on it's what the temperature of my moderator, like the average temperature, is where this Maxwellian peak is. And if I increase the temperature of my moderator, what it effectively does is it takes this peak and it shifts it to the right. So it's going to shift to the right, but only in the thermal region. In the thermal region. And we had talked about this before, but it's coming back up again now. So I wanted to just make sure that we like kind of revisited that. And on the next slide, I'll hopefully be able to convince you why it's only the Maxwellian part of the distribution that gets shifted and not any of these other parts. But so if in the intermediate range, that's where those resonances are, where you get more likelihood of parasitic capture of my neutrons. So if I've taken this Maxwellian and I've shifted it to the right, that means that my energy spectrum for these thermal neutrons is like getting kind of closer to that resonance region where it's more likely that some of those neutrons get captured in some of those like lower lying resonances in this resonance region. That more parasitic capture means my capture to fission ratio goes up. And that means that if I increase temperature, because of the spectrum shifting to the right and that increasing the capture to fission ratio, it ends up decreasing the reactivity. So that makes my moderator temperature coefficient more negative. So this is a thing that this is an impact to the microscopic cross sections due to a temperature change. But also we can be impacting the density, the mass density of our coolant as well. So if you increase the temperature of something, does that make that material expand or contract when you increase the temperature? Perfect. So that coolant is going to expand. If you're expanding, what does that do to your density? Does it go up or down? It makes the density go down. So the density will decrease. Because if you're expanding, it means that your volume is increasing, but the mass is staying the same. Like if you take a pot of water and you put it on the stove, then you've got the same amount of water there. But as that water heats up, that water expands like within its container, which means that same mass, larger volume, so the density goes down. And then voids start forming. When the voids form, that means that you get less moderation because the steam is a less effective moderator than the water itself. If you get less moderation, then less neutrons can make it into the thermal spectrum where they're likely to fission. So it means that we get less thermal fissions. And if neutrons are less able to be moderated, it means that they might spend more time in the intermediate range where they're more likely to get captured by a resonance. So that means that we end up getting more resonance absorption. And so in that case, if we think about the void coefficient for like a water moderated core, it's going to be large and negative. So it's large and negative. And I think the thing that's the dominant effect is this expansion for our moderator. It's more influenced by the expansion than it is of the shifting of the neutron spectrum. But both of those end up being a negative, so they both end up kind of affecting the temperature or the moderator temperature coefficient in the same direction. So this is that plot that I was very crudely illustrating on the previous slide, where this is our neutron energy spectrum as a function of energy. You've got the thermal energy range, which looks like a Maxwellian distribution. You've got the fast energy range, which looks like the fission spectrum. And what we were saying before is that if you increase or decrease the moderator temperature, the only part of the energy distribution that's impacted is the thermal part. So the only part that's impacted is the thermal range. And that thermal range, that's the thing that looks like the Maxwellian, which is M of E. And when we talk about thermal neutrons, what we're saying is that these neutrons are in thermal equilibrium with the moderator. So like this Maxwellian has a peak, and the peak, the energy of that peak, this energy, that's like the average energy of my um that this is an energy that corresponds to the average temperature of the neutrons in my system being in thermal equilibrium with the environment. And so that energy is going to be like a K, which is Boltzmann's constant, times the T average of the average of the moderator. So if the moderator is at some average temperature and I multiply that by K, that gives me the average energy of the neutrons that are in that system that are in thermal equilibrium with the moderator. And so if I increase the average temperature of my moderator, that means that the E average goes up, so that gets shifted to the right. So this whole peak would get shifted to the right if my temperature would increase, and it would get shifted to the left if my temperature would decrease. So an increase in temperature shifts me to the right, and a decrease in temperature shifts me to the left. And so what we're saying is changing the moderator temperature only affects the Maxwellian. And to illustrate why that is, it's helpful to just kind of think about like doing a hand calculation of what would be like the highest temperature that my moderator could have, or what temperature, like highest temperature my reactor in general could have, and also to think about the fact that what kind of, if I look at the energy axis, what kind of scale is this axis on? Perfect. It's on a log scale. And notice that this is like 10 to the 7 right around here at the end of the fast part. And this is like 10 to the negative 3-ish here where it kind of starts to hit 0 in the thermal part. So it spans from 10 to the 7 to 10 to the negative 3, which means it spans 10 orders of magnitude. And my temperatures can't change by 10 orders of magnitude if I compare like room temperature or average temperature to like which is in this region relative to like what the temperatures would be if I was calculating a KT for the neutrons that are fast. So on the next slide, I want to try to convince you about why it's only the Maxwellian part that gets shifted. And so the neutrons in the Maxwellian are in thermal equilibrium with the reactor, and they have an energy that's proportional to K times T, where K is this Boltzmann constant in units of EV per Kelvin. And so to see where like that thermal range would stop, we just maybe want to ask the question, what's the highest temperature that our fuel and therefore our reactor could ever really get to before we had like very serious problems? What would be like kind of the limiting temperature of the fuel in our reactor before things get really, really bad? Perfect. Yeah. So it corresponds to the whoops, corresponds to the T to the melting point. And so if that peak of the Maxwellian is at the average temperature of my reactor, then the highest that average temperature could ever be until like the reactor is basically a big old pile of corium, then that temperature, at least for UO2, is about 2800 Celsius. So if I take this 2800 Celsius and I convert it to Kelvin, and then I do K times that temperature in Kelvin, that's going to give me like the maximum energy of the thermal part of my spectrum. And if I multiply those two things together, I get about, so what I'm saying is if I do K times T melt, where that T melt is in Kelvin, then this is going to come out to about 0.26 EV. So if my reactor was melted down, that thermal peak would be about 0.26 EV. So in general, what we can say is that like if the energy is anything less than 1 EV, that energy is so high that it can't really be related to the temperature of my materials. It has to be related to just how fast the neutrons are going, not being in thermal equilibrium. They're born very fast, so they're born with a very high energy. They thermalize and they slow down, and eventually they get into thermal equilibrium with their environment. And so any energy is less than 1 EV. 1 EV is kind of like where we can say is the cutoff of our thermal range. And so any higher energies than that aren't going to be due to temperature. They're going to be unaffected by it. Anything above 1 EV is going to be unaffected by temperature changes of my system. So previously, we've been talking about liquid moderated cores. There's other reactors that use solid moderators. The most common solid moderator is graphite. So that's what the RBMK uses. That's what molten salt reactors use. Gas-cooled reactors, they all use graphite as the moderator. Um, and a solid, when it heats up, doesn't really expand as much as a liquid would. So for solid moderators, their reactivity impact is mostly due to Doppler, to the shifting of the Maxwellian, and that shifting of that Maxwellian to the right, allowing for more parasitic capture in those low-lying resonances. That's what ends up dominating the graphite, a solid moderator temperature of temperature coefficient. Um, and in general, those moderator temperatures are kind of complicated. It depends on a lot of complicated interactions, which makes that temperature dependence a little bit harder to talk about. But Oh, and I guess just in terms of a terminology, you might see if you're reading like in the Stedkov notes, they might talk about the shifting of the energy spectrum to the right um, as hardening. And it's just two different ways of saying the same thing. If the neutrons have a higher energy spectrum or get shifted into a higher energy, they refer to that as hardening. So you might see like an increase in the moderator temperature results in a hardening of the neutron spectrum. It just means that it gets shifted to the right. So this is just kind of illustrating what the temperature coefficient would look like in terms of a feedback response. So what we're saying is that like we're imagining a reactor that's critical at like say 1 megawatt, and then it gets a positive reactivity insertion from the removal of a control rod. And so if I have a positive reactivity insertion into a reactor that was initially critical, then the immediate response is that the power is going to jump. So I'm going to have a prompt jump in power. And that prompt jump in power is then going to cause the fuel temperature to increase. And depending on the temperature coefficient of my system is going to influence what this positive temperature change does to my system. So if the temperature coefficient is positive, then increasing that power increases temperature, which increases reactivity. And if I increase reactivity more, that increases my power more. And then that is going to be like a vicious cycle that kind of continues and feeds on itself and causes things to blow up. So that's bad. We don't want the temperature coefficient to be positive. If the temperature coefficient is negative, then when we increase power, we increase temperature. But if the temperature coefficient is negative, increasing the temperature reduces the reactivity. And if that positive reactivity can get balanced by that negative feedback, then eventually my reactor can settle back into a new steady state. Eventually, those feedback effects will make it such that my reactor could settle into a new steady state if that temperature coefficient was like small-ish, or if the heat could be removed relatively quickly. And then if that temperature coefficient is very negative, then you could get something called a power overshoot, where you get like a smallish increase in temperature that causes a very rapid decrease in reactivity to the point where you might end up going subcritical, and you might end up taking your system to like a new steady state, but that's at a much lower power level than what you started with. So this is kind of illustrating those three cases on a graph, where that's what would this is my initial power, and then this is how the system responds to a positive insertion depending on what my temperature coefficient is. My temperature coefficient is positive, then my system basically exponentially increases. If that temperature coefficient is like negative but not super negative, then we increase, but we end up leveling out. The power increases but ends up leveling out to a new steady state. And if I have a very negative temperature coefficient, it could cause a power overshoot where my power goes up, but then this increase in power and increase in temperature causes so much negative reactivity to be added that I get a significant drop in my power as a result of that highly negative feedback. Um, this is just a table that illustrates some temperature coefficients of reactivity for various reactor types. And notice that like the pressurized water reactors have the temperature coefficient that's the most negative at the highest magnitude. And then all of these other reactor types have still negative, but not as negative as like the PWR or the pool type water reactors. So in general, water ends up being something that adds a negative reactivity has a negative reactivity coefficient associated with it. So this is just kind of making us think about what we've been talking about, to imagine what if we had a reactor that had a positive feedback effect. So this is a picture of a reactor that has graphite as a moderator and water as a coolant. And so technically this is also a boiling water reactor, in that as the coolant goes through these fuel channels, it boils, which produces voids, which then allows steam to be generated, which turns a turbine and does all that fun stuff. So in this case, most of the moderation comes from the graphite, but and the water is like mostly a working fluid that is used as like the heat transfer medium. But because it's water, it still has some moderating ability. And so because it uses graphite as a moderator and water as a coolant, you kind of have a lot of extra, you have almost more moderation than you might need, which means that with extra moderation, you can get away with using lower enrichment. So this reactor could actually run on like 2% enrichment, which makes your fuel costs lower. And so we want to imagine that this reactor is critical, and then for some reason, there's an increase in power. And so if the power level goes up, it means that my temperature is going to go up, and it's going to cause more steam to be produced. And if I have more steam, then that means that that water ends up absorbing less than it would have before. So like I have graphite that's moderating things. I have water that's like moderating things, but also if you look at this table of moderator data, if you compare water and carbon, water has a lower moderating ratio because the sigma A for water ends up being relatively large compared to the sigma A for carbon, which is what graphite is made out of. So water kind of does a decent amount of absorption. And if we were critical before, then now that we've if we're critical before, it means our production losses were balanced with water doing the amount of absorption it was before the power increased. Then power goes up, which makes temperature go up, which produces all these voids. And those voids mean less absorption within the water. But if I have less absorption than I had before, that means that now my production is greater than my losses. And so the power, so the K effective goes above 1. It goes super critical. And if my reaction rates for fission go up because I'm now supercritical, that means that my power is going to increase more, which means my steam is going to increase more, which I'm going to get more voids and less absorption, and then more fission, and then more power. And that cycle is going to continue indefinitely. So this is an example of a reactor that has a positive void coefficient. And the reactor that this is talking about is the RBMK reactor. And in 1986, in Pripyat, which is like modern day Ukraine, these above series of events happened. The power increased so much that basically all of the water, like almost instantaneously, flashed into steam, which caused a steam explosion. That steam explosion ended up causing a hydrogen explosion, probably because of the cladding becoming like you have the hydrogen and zirconium and the cladding basically separating from each other, and you basically just got like pure hydrogen, which ended up interacting with the water, with the air that was brought into the system because of the steam explosion. So then you got a hydrogen explosion as well, and there was a full meltdown. Worst nuclear accident that's ever happened, and that was what happened to the Chernobyl reactor. Um, so good example of why you don't want a positive void coefficient in your reactor. Um, and so yeah, that's what could happen if you aren't aware of the kinds of coefficients that your reactors have, and also if you like are operating those kinds of reactors irresponsibly, which is certainly what they were doing during Chernobyl. Um, so in terms of like operating a reactor with feedback, you kind of have to be aware of the fact that reactors do have feedback, which means that like as you try to change the power level of your reactor, you kind of have like a series of steps that you have to go through because every time you do something to increase power, that's going to impact temperature, which is going to then probably have a negative feedback effect, which would then cause your power to like end up going back down. So this is like kind of illustrating that you've got your control rods such that you're critical, but at like a very low power and at a low temperature, and you want to like turn this reactor up to full power. So um, to get to a higher power means I need a higher fission rate, and that means that I need a higher temperature. And so, but if I try to like increase my temperature and I have negative feedback, then increasing that temperature is going to cause my reactivity to go down. And so lots of power reactors end up having feed water heaters, which can be used to get the water temperature to the operating point that it needs to have. And then as you're like kind of heating up your coolant, you're also gradually removing those control rods so that the negative reactivity from the temperature increase is balanced by the reactivity that you're removing from pulling those control rods out. And you kind of have a series of like temperature increase, control rod move out, temperature increase, control rod move out, so that you can eventually get to a point where you get to like the hot condition at full power. And so the final control rod position would be the hot critical state, where those control rods are removed more than they were when you were at the cold critical state. So if we wanted to like go through a series of step changes to our system, and we knew some information of our reactor at state one, and then we knew some information about our reactor at state two, we could use that information to then approximate what our feedback coefficient would be. So we'll say that state one, we know the reactivity and we know the temperature. So we've got some, or we'll say we've got some K effective at state one, and we've got some temperature at state one. And then some later state, we have a new value for the K effective. So we've got a K effective at state two and a temperature at state two. And then we already know that that reactivity can be written in terms of K effective, that the reactivity in state one is going to be K, I'm just going to say K at state one minus one over the K at state one. And then the reactivity at state two would be the K at state two minus one over the K at state two. And if these are my initial and final reactivities, and I know my initial and final temperatures, then I could approximate that temperature coefficient of reactivity as just being the change in reactivity over the change in temperature. So that means final reactivity minus initial reactivity over final temperature minus initial temperature. So that would mean like putting the final reactivity initial in terms of K would mean I've got K2 minus 1 over K2 minus K1 minus 1 over K1. And then that's all divided by the temperature at state 2 minus the temperature at state 1. So this is final reactivity minus initial reactivity over final temperature minus initial temperature. And then from there, you can kind of simplify the numerator by like getting a common denominator between these two terms. And then once you have a common denominator, you can add the numerators. And when you add the numerators, the you're gonna think things are gonna simplify. Um, and so the way that this will end up looking, this T2 minus T1 is just my delta T. So this is going to be 1 over delta T times, and then in the numerator, I'm just going to end up with K2 minus K1 over K2 times K1. So that would be how I could approximate my alpha T. Just knowing information about those initial and final states, that would be how I could approximate that temperature coefficient. So that's example kind of like going along with a series of steps to get to a new power. This would be like probably something that you would do if you take like the nuclear engineering experiments class in senior year, then that's like one of the experiments that you can do, and you'll end up like measuring the temperature coefficient of the trigger reactor. Um, and this kind of like going from one state to another and then doing a calculation, that's one way that you could go about finding your reactivity coefficient. And the other way to do it is using something called perturbation theory. So this is like a more like mathematical way of determining a temperature coefficient without having to do like a series of steps at different states. All you really need to, oops, all you need to have to do perturbation theory is that you need the reactor system to be like initially critical or near critical. And the changes that we make to the system to go from state 1 to 2 have to be small enough that we can treat those as small perturbations. And in the language of perturbation theory, the initial system before we add a perturbation is called the unperturbed system. And we use a subscript U for any of our unperturbed quantities, like before the change was made. And then there's going to be some perturbation to our system. Like, for example, there might be a perturbation in the K effective, which perturbs the K effective by some small amount. And so that's what the delta K effective is. It would be some small perturbation in K effective. And then we call the final system the perturbed system. And for perturbed quantities, we use a subscript P. So on the next slide, it kind of outlines what our unperturbed system would look like as a criticality eigenvalue problem, where L is our loss operator, Q is our gain operator, and we're writing this as a eigenvalue problem. So we have like a 1 over k in front of the gain operator, and this is the unperturbed system. So all of these quantities have a subscript U attached to them. And because the reactor is initially critical, that means that our unperturbed flux, it might depend on position and energy, but it doesn't depend on time because we're looking at a criticality condition. We're doing an eigenvalue problem where there's no time dependence. And so these perturbations could be made to like any quantity in our system. And by definition, the perturbed quantity is the unperturbed quantity plus whatever perturbation we made to that quantity. So this would be the perturbation in our loss operator. This would be the perturbation in our gain operator. This would be the perturbation in our scalar flux. And this would be the perturbed K effective. And these perturbed states are always the unperturbed state plus whatever the perturbation that was made to take me from that unperturbed state to the perturbed state. And then the resulting critical system in the perturbed case is basically the same as the unperturbed, but I've just got P's because it's the perturbed state. And if we can assume one group diffusion, then we can like get pretty nice analytical expressions for the perturbation in K effective due to the perturbations in various quantities that might change to our system that would impact K effective, like changes in the absorption cross section or the diffusion coefficient or the product of nu and sigma f. So like if you use first order perturbation theory, then you can get this, and you don't have to derive this equation. This equation would just be given to you, and then our goal would be to like try to use it to see to learn some things from it. And so this is the perturbation in K effective due to some perturbations in various quantities. So you could have a perturbation in nu f sigma f, you could have a perturbation in sigma a, you could have a perturbation in the diffusion coefficient, and by perturbing those inputs, those things are going to affect the multiplication factor of the system. And so if you know what those perturbations are, and you know what the unperturbed values are by doing like a critical reactor analysis before you made the perturbations, then you can use 7.2.3 to see how K effective is impacted in terms of how it gets perturbed by these various perturbations and other properties of our system. And by definition, we could actually take this equation, instead of writing it in terms of a change in K effective or a perturbation in K effective, we could write it in terms of a perturbation in the reactivity. And so basically what we're going to say is that by definition, if I'm taking the derivative of the reactivity, that's the same thing as the derivative of K minus 1 over K. And by definition, well, really, K minus 1 over K, I can simplify that by just breaking this up into two fractions. Outside of a common denominator. So that would be the derivative of 1 minus 1 over k. And then the derivative of this is just the same thing as the derivative of 1 minus k, because the derivative of 1 is 0. So this would be the same thing as negative derivative of 1 over k. And then if I'm doing the derivative of 1 over k, that is going to be, I'm going to have a negative times negative 1 over k squared. And then I also multiply it by the derivative of k itself. So that's just kind of like doing a chain rule where I'm doing the derivative of the outside function, keeping the inside the same. So that's the negative 1 over k squared. But then I'm also multiplying by the derivative of that function itself. And these negatives end up canceling each other. So then what this ends up looking like is dk over k squared. And really, I could have put my effective and my effective here. And so notice that on 7.2.3, if I were to divide both sides by k squared, then on the left side, I would have the derivative of k, or the perturbation in k, divided by k effective squared. And that's exactly what I have here, which is exactly what this reactivity change is. So then by definition, I can rewrite 7.2.3 in terms of a reactivity perturbation instead of as a K effective perturbation. And then we can take this as like kind of like our governing equation, and we can do some like kind of examples with it. So the first one that we want to consider is if we have this critical system and then we add some absorber to the system, which gives me a perturbation in my absorption cross-section. So if this absorber only perturbs K, the sigma A, then that means that the perturbed value of sigma A is going to be, it's going to be the unperturbed value, sigma A. How did I write this? Sigma A unperturbed, which could depend on position, plus the delta or the perturbation in sigma A. So my perturbed value is my unperturbed value plus that little delta. And if it's only the absorption cross-section that's being perturbed, it follows that the perturbation in nu f sigma f and the perturbation in the diffusion coefficient are both 0. So if the perturbation in nu f sigma f is 0, and the perturbation in my diffusion coefficient is 0, that means that this first part of this integral goes to 0, and also this last part of this integral goes to 0. So ultimately, what this is going to look like is I'm going to have negative integral over the volume of, with respect to volume, of that perturbation in sigma A times that unperturbed flux squared. And then it's all going to be divided by the denominator. And the denominator isn't going to change. So that'll be a volume integral dv of nu f sigma f unperturbed times phi unperturbed squared. So that's how you could predict what change in reactivity you're going to have based on that perturbation in the absorption cross-section. And these unperturbed fluxes, those would come just from like using the models that we have for one group diffusion. Like if it's a sphere, or if it's a cube, or if it's a rectangular parallel pipette, then you know what those flux, what the scalar flux looks like before the perturbation, when like we can assume the reactor was critical. And then if you know what that shape is, and you know what this little absorption perturbation is, then you can work out what the perturbation in the reactivity is without having to do static calculations from one state to another. Which one? Oh, this guy? Oh, yeah, that's just this notation for basically like a perturbation. So it's kind of like the same, it's this same notation, which is this same notation. So that's just the symbol for a perturbation. Yeah. And I mean, you can basically think of the perturbation as kind of like a small change. And so this is another example of a perturbation theory example where in this case, we're assuming that we've got it says infinite slab reactor. It's the same thing as a 1D reactor where it's a rectangular geometry that's infinite in Y and Z and then is finite in X. And in one group diffusion, we have a formula for the flux in a 1D slab. And we're going to assume that we perturb the system by adding control rods into some depth h into this slab. And so we want to determine how the reactivity is perturbed by this added absorber. So the perturbation of the absorber, we could think of it as kind of like a piecewise function where it's a value which is just delta sigma A in the range where we've added that absorber, which would be from like x equals 0 to how high that control rod is. And then everywhere where that absorber is not there, then the perturbation has no effect. So the perturbation would be 0 from H up to A. And there's two kind of different ways that you can write this because there's two different ways that you could write the flux for a 1D slab reactor. Um, in our tables and what's shown in Svedkov's notes is that 1D slab looks like a cosine distribution, but the domain of our reactor goes from negative A over 2 to A over 2. And this works because then at negative A over 2, the cosine of this evaluated at negative A over 2 gives you, it ends up being 0. And then evaluating at positive A over 2 also gives you 0. And then it gives you a maximum in the middle, which is B at x equals 0. But there's nothing stopping us from writing this distribution in terms of a sine function as well. We just end up having to change the bounds of where we define our 0 in our reactor boundary. So these two are exactly equivalent. And like, so if you want to do this calculation, you basically need your limits or your geometry bounds to be the same. So we could either work with these two pieces together or we could work with these two pieces together. We just kind of need to pick the ones that have the same coordinates. So this would be how you could write this perturbation in terms of x going from negative a over 2 to positive a over 2. And ultimately, if you do it either way, you'll get the same answer, but it's a lot nicer if we use these results with the sine function, because then the reactor is defined from 0 to A, and then the absorber is entered at a height at a depth of h into the system. So the perturbation is there from 0 to h, and then from h up to a, it's a 0. So I'm just going to write that definition of the reactivity change that we just came up with. And then in for the flux, I'm going to plug in this definition of the unperturbed flux for this geometry. And in the numerator, remember that these are both integrated over the volume, but if it's a 1D slab, then dv just becomes dx. And then the bounds on this first integral are going to it's either going to be from 0 to a, or and like if you did 0 to a, you would get the right answer. You would just have to recognize that delta sigma a is non-zero only from 0 to h. So if I'm multiplying these two things together, this integral is going to be 0 for any values of x that are greater than h. So instead of this first integral going from 0 to a, this first integral actually just goes from 0 to h. Whereas the second integral is over the entire volume. So the second integral goes from 0 all the way up to the side length a of the reactant. And then notice that both of these, the flux magnitude is a constant, which could get pulled out of both integrals and then would cancel on top and bottom. This perturbation is a constant over this range, so this perturbation can come out front, and nu f sigma f unperturbed is also a constant, so it could also come out in front. So I'm going to have negative delta sigma a over nu f sigma f unperturbed. And then I'm going to have what's left over of these two integrals. So I'm going to have integral 0 to h of sine squared pi x over a dx in the top. And then in the bottom, I'm going to have that same integral, but going from 0 all the way up to a. I've got a sine squared pi x over a dx. So if I can integrate a sine squared, then I can get an analytical expression for what this reactivity insertion is. And to integrate this analytically, you just want to make this trig identity substitution so that you can write sine squared in terms of cosine of 2x plus a constant. And then you can do a u sub to evaluate this integral if it's a cosine without a square on top. So if you do that integration of this quantity right here, this is the expression that you would get for that reactivity perturbation. And so that's like a good calculus refresher. It would be good to go through those steps and make sure that you can get this answer yourself. It's just making that substitution and then doing a u sub for those integrals, and just being careful about the bounds because they have different bounds. And when we talk about a reactivity change due to like adding a control rod into our system, the reactivity change due to the absorber is referred to as the absorber's worth. The absorber's worth. Like you might hear the phrase control rod worth, which would be some number with units of like PCM or dollars, and that's basically telling you how much reactivity removal or what the reactivity effect is if you were to like fully insert or fully remove that control rod from your react. And I think that's everything I wanted to say about perturbation theory. The only other thing I really wanted to talk about was uncertainty, because uncertainty in our quantities that we're measuring could cause a perturbation to our system if we're like unaware of what that uncertainty is. And so if we have quantities that we're measuring, we want to be able to compute what's the uncertainty of that quantity based on uncertainties in other quantities. So like if we have some function f that's a function of multiple variables, x1, x2, all the way up to xn, and each of these inputs has their own errors at delta x1, delta x2, delta xn, then the formula for the uncertainty or the error in that original function is going to be a bunch of multiples of the derivatives of my function with respect to each quantity times the uncertainty in that quantity. So it's going to look like uncertainty, derivative of my function with respect to that first, with respect to x1 times the delta of x1 squared. So the derivative of the function with respect to that first variable times the error in that first variable, that whole quantity squared. And then I would do that for every variable. So I do the derivative of my function with respect to the second variable times the uncertainty in that second variable squared. And then I'll just say plus dot dot dot. I would do this for all of the quantities that have input uncertainty all the way up to xn. So this would be the derivative of f with respect to the derivative of xn times the delta or the uncertainty of xn squared. That's just like your standard error propagation formula. Hopefully we remember that from like the detector lab. And so like if the quantity you're talking about is k infinity, then k affinity is nu f times sigma a. So you might have some uncertainty in k infinity if you have uncertainties in these individual quantities. And if there's uncertainties in these individual quantities, this is the relation, this is the formula that you could use to say what's the uncertainty in k infinity based on the uncertainties in any of these quantities that I have. And this is helpful for lots of reasons, including you have a problem set question. I think it's problem set 6, number 5, that talks about finding the error in your critical mass of a geometry of a sphere due to some uncertainty in the k effective of that material. And so in general, you kind of have these are some hints that'll get you through that. Um, we know that the uncertainty or that the error in my reactivity can be written in terms of the error in my k effective. We know what the formula for k effective is, and we know that bg squared for a sphere is pi over big R squared. And so if we plug this definition in here, that would allow us to get the radius r as a function of k effective, k infinity, and L. And so once you take that and isolate r, then you can relate the dimensions to the mass because of the definition of density, that the mass density is the mass of the reactor divided by the volume, which in this case would be the volume of a sphere. So I could take this definition for R, I could convert it into a volume by doing 4/3 pi R cubed, and then I can get this mass by itself. I would get the mass of my reactor in terms of all of these reactor properties and the mass density of that material. And then I would use my error propagation form. And my uncertainty and my mass, oh, just real quick, this would be the derivative of my mass with respect to the derivative of k effective times the uncertainty in k effective quantity squared. And so that uncertainty in k effective is just like some input that you're going to assume that you know. You're going to take this relationship that you would get for the mass, which ends up depending on k effective and some other things, but you're only assuming that the uncertainty in the mass is due to that uncertainty in k effective. You'll take this definition and you'll take the derivative, you'll multiply by that uncertainty in k effective, and that'll get you the uncertainty in your mass due to that uncertainty in k effective. So those are kind of like the steps that you would go through to get that final expression, and that's how you would get that solution in that last part of the problem set. So yeah, that concludes lecture 13. That also concludes our exam 2 coverage. So exam 2 will stop there. When we come into class tomorrow or on Wednesday, we'll cover new stuff, but that new stuff won't be on the second exam. It will be on the final though. And so yeah, if y'all have questions for me, let me know. Otherwise, I hope you'll have a good rest of your day. I do have your quizzes from the last quiz, so just stick around for a second. I'll pass those out to you.